Yes, indeed, it's a good time to record. Let me try and see if I should probably share the screen. So summer school at ICMU in functional isoperimetry, let's say, and related high-dimensional phenomenon. And so let me start by reminding you something that you probably know. Can you see me? Can you see the board? Can you see everything? Can you see the screen? Please give me some feedback on what you guys see. Is everything okay? Все видно, дуже добре. Так, another thing is also if somebody doesn't understand something I said in English, please feel free to ask in Ukrainian and I can repeat something in Ukrainian. I'd be very happy to do that as well. So here is a toy question that originates, that dates back to ancient Greece or ancient Rome. I would say Greece. Imagine that you're an ancient soldier and you fought very bravely in battles, and for all your heroic achievements, you're given a huge, very long rope, and you're told that you need to surround the field with this rope. So surround a field with it where you can build your house and live, and this will be your land that will be given to you for all your heroic achievements. What would you do with this rope if you want to surround as much field as possible? So you want a plot of land as big as possible with this very fixed rope. What would you do? Any ideas?
I would make a ball.
You'd make a ball, exactly. Or, well, we're on the field, right? So you'd make a circle. So indeed, the best thing to do is, well, so my drawing's not very good, but ideal solution is to make a circle with this rope, because if you fix the circumference, the largest area will be that of a circle or of a disk of all the shapes with the same circumference. And that is the content of the classical isoperimetric inequality. So as I said, it dates back to the ancient times. Perhaps the first modern times mention of it is in 1837 by Steiner, but rigorous proofs, Steiner proofs were still lacking, so rigorous proofs were still done in the 20th century. We will prove it very soon, very easily, actually. And the isoperimetric inequality tells you that of all the regions, so in the same way as you can say if you prescribe the perimeter and want to maximize the area, the circle wins. Alternatively, you can say that you want to prescribe the area and minimize the perimeter, and that's when the circle wins. So of all the shapes of fixed area, the disk or circle has the smallest perimeter. So if you have a shape like this of area 1 and the disk of area 1, the perimeter of the disk, the circumference, is going to be smaller. More generally, the same thing is true in high dimensions. Let's denote, let's consider Rn, an n-dimensional Euclidean space. And in Rn, we will consider a unit ball, n-dimensional ball. It's a collection of points x in Rn such that the length is smaller than 1. Here, length of a point, same as sometimes is denoted as L2 norm, is square root of the sum of its coordinates, squares of its coordinates, sorry. So in Rn, we look at all the points, all the vectors whose length is smaller than 1. And that's what the unit ball, the ball of radius 1 is. We denoted B2n. And the isoperimetric inequality says, theorem, the isoperimetric inequality, it says that if, so this is again like a little bit informally, let's say informally. Suppose K in Rn is a measurable set. Suppose the volume, n-dimensional volume of K this is an n-dimensional volume, is the same as n-dimensional volume of the unit ball, the ball of radius 1. Then the perimeter of K perimeter of K that we'll discuss in a minute is going to be bigger than the perimeter of the ball. Here, the perimeter of K is defined in the following way. So if this is my set K, I look at the thin strip, thin annulus around K of all the points that are distance epsilon to K, that are of all the points that are not in K, but are distance smaller than epsilon to K. And so the perimeter of K is informally this, the volume of this epsilon annulus that I will define in a minute, divided by epsilon in the limit, of course. So the most important thing will be right now is to define formally how will we make sense out of this annulus. But this is so far just a picture. So let me ask you, are you guys following what I'm saying? Does this make sense? Let me look back because everyone's very quiet. Let me see. So does anyone have any questions? So the parametric inequality in Rn says that of all the sets of fixed volume of the same volume as the volume of a ball, the ball has the smallest perimeter or the smallest surface area. Any questions? So in order to, well, prove this, we need to make sense of what it is, of what the perimeter is. And I'm telling you that the perimeter is the limit when epsilon goes to 0 of 1 over epsilon times the volume of an epsilon annulus around our set K. Now, in order to define this epsilon annulus, I would like to introduce another definition, something that is called Minkowski addition of sets. Suppose A and B are sets in Rn or any group, but we will be working in Rn throughout. So suppose A and B are sets in Rn. A plus B is a collection of points of the form A plus B, where A is in A and B is in B. So Minkowski sum of sets is just a set consisting of sums of vectors where vectors are taken from these two sets correspondingly. Any questions about this? So let's consider some examples. Let's try and consider an addition of a square and the ball, for example, little bit. How will this look? Let me try and draw my square. And to the square, add all the vectors in the ball. To each vector in the square, I add all the vectors in the ball. It means that around every point on the square, I draw this ball and I add to all of these vectors in the square, all of the vectors in the ball. So I draw my ball here, and here, and here, and here, and it's as if I basically move my ball around like this. And I get sort of a square with round corners. All right, that's one example of Minkowski addition. What happens if I add, I don't know, like a triangle like this with center at the origin and a triangle like this at the center at the origin? Can somebody, by the way, if anyone has a device that can draw, you can also draw here. I can allow you to scribble. You see, I can allow guests to scribble for a second. Maybe somebody can try and draw what comes out. Or if not, then say it in words.
Is it a hexagon?
Yeah, exactly. Very good. It's going to be a hexagon. So basically, again, we draw our triangle, and around each point, I draw the same triangle but flipped. I sort of move my flipped triangle around my triangle everywhere through all of the points of it. And yeah, this is what I get as a result, I think. This is what Minkowski addition is. You take two shapes, you move one around the other because you add all pairs of vectors, and yeah, that's what you get. So this enables us to understand better the surface area, this perimeter, the annulus that I was drawing earlier. So now formal definition of perimeter. Formal definition of perimeter, by the way, strictly speaking, there is a number of definitions of perimeter that in principle for sets which are very bad don't always coincide, but we will consider sets which are very nice. in which case also definitions coincide, and we will just basically take this definition for our perimeter as the main definition. So formal definition of perimeter, or surface area. Sometimes it's called also surface area. So suppose K in Rn is a set, measurable set, let's say, Borel measurable set. When I say measurable, I usually consider Borel measurable. Let's consider the set K plus epsilon times the unit ball. Let me draw what comes out. So if this is my set K, let's draw it like this, why not? Let me prohibit guests from scribbling again, and you guys are allowed to scroll up and down in your browsers. As I said, if you follow the link that I sent in the chat, let me send this link again just in case. You will be able to follow everything I say throughout. Yes, make a circle. I see some people wrote, so if you have something to say as an answer to something that I ask, for instance, I really strongly encourage you to speak up with voice, because I don't see the chat, right? So please say it out loud. It's also really important for me to hear you sometimes and not just hear my own voice all the time. So let's consider K plus epsilon ball. So we have a set K, and I take a little tiny ball of radius epsilon and move it around. Around my set K. This is what I get. Next, I throw away here set minus. I throw away the set K itself. So let me make it like this. Actually, highlight what I'm left with. I'm left with everything that's distance epsilon to K, K plus epsilon ball, but not set K itself. So this is my epsilon analysis of K. This is the set that I'm looking at, K plus epsilon ball minus K. Next, what I do is I consider n-dimensional volume of the set of this annulus, and I divide it by epsilon. So I divide this shape that I highlighted with purple by epsilon here. So what I'm left with, as you might guess, is roughly precisely the perimeter of the set K. Now I have to take not the limit, but formally lim inf when epsilon goes to 0. And that is what is defined to be the perimeter of K. This is a definition. Let me maybe write it here, sorry for the mess. This is the formal definition of perimeter of a set. Are there any questions about this formal definition?
So do we take lim inf here because in general limit doesn't exist?
Yeah, so for very, very bad sets, you're absolutely right. Yeah, for very bad sets, hypothetically, limit might not exist. So to be on the safe side, in order to not have to prove the existence of the limit, in situations that we're considering, we're taking limit. But just mind that in principle, limit will typically exist for the sets that we consider. So pretty much just don't worry about this if possible. Thanks for your question. Any other questions? So this is a perimeter of a set. So isoperimetric inequality tells us that if the volume of K is the same as the volume of Euclidean ball, then the perimeter of K is bigger. Now let me reformulate it a bit. So let's recall an important fact about Lebesgue measure. And that's a homogeneity property. So if I take my set K, let's say this is my set K, and I inflate it by a factor of 2, for example, I consider a set 2K. More generally, if T is bigger than 0, TK, I will consider to be the set of Tx, where X is in K. So I just inflate a set by a factor. What can I say about the volume of Tk in terms of the volume of K? Can somebody tell me?
It will increase by t to the power of dimension.
Exactly. It's gonna be it's gonna get multiplied by t to the power n. So on the line, if I have a linear segment and I double it, obviously the length will double. On the plane, if I have a square and I double it, the area will quadruple. On the space, three-dimensional space, if I double the cube, clearly I will have 8 little cubes. And in generally, Lebesgue measure, it's called n-homogeneous. That means that if I multiply a set by a factor of t, if I inflate it by a factor of t, the volume increases by a factor of t to the power n. Now, another important thing, what can you say about perimeter? What do you think about perimeter? What if I take a set tk instead of k? What can you say about the perimeter of tk? Or surface area?
It will increase by t to the power n minus 1.
Exactly. It will get multiplied by t to the power n minus 1, not n, because perimeter is an n minus 1 dimensional object in a way. So you can think about a circle, that if I double a circle, its circumradius is pi r. If I double it, if here I have 2r, here we have 2 pi r. So if I double my circle, the perimeter will get multiplied by a factor of 2, not 4, right? Because the perimeter of a set is an n minus 1 dimensional object. So another reformulation of the isoperimetric inequality is that if K is any set, let's not put any restrictions on it. Let's not say that we fix its volume. Let's just say that, okay, I'm a little bit concerned that my pencil wouldn't be writing. Let's see. Okay, so perimeter of a set K over the n-dimensional volume of set K to the power n minus 1 over n will always be bounded from below by the perimeter of a ball of any radius, actually, but let's say unit 1, divided by the same volume quantity. So this is for any set K in Rn. So this formulation of the isoperimetric inequality is now actually homogeneity free. So instead of assuming that the volume of K is fixed, we can just assume, well, that it's arbitrary and we rescale it appropriately. Let me leave it as a little homework that this is indeed just a formulation of the isoperimetric inequality in view of this homogeneity properties, if that's okay. Any questions up to now? So in order to prove this isoperimetric inequality, we will discuss now our next little thing. So this was, let's say, first little bit related to the isoperimetric inequality. Let's discuss next little bit, and of course we'll come back to the isoperimetric inequality imminently. But the next little bit is called the Brun-Minkowski inequality. The Brun-Minkowski inequality. Has any of you ever heard about the Brun-Minkowski inequality? Don't hesitate. As I mentioned, I'm very happy to always hear from you guys. So in any case, so the Brun-Minkowski, let me then formulate it. So the Brun-Minkowski inequality tells us that if K and L, so this is the theorem, Brun-Minkowski, if K and L in Rn are Borel measurable sets, Borel measurable, then the volume of K plus L to the power 1 over n is bigger than the volume of K to the power 1 over n plus the volume of L to the power 1 over n. This is the Brun-Minkowski inequality. Now, minor comment, actually, I'm a little bit annoyed with myself. Let me use the notations that I'm used to. Notation, if that's okay. Volume in n dimensions of a set K. Standard notation is well nk. Sometimes I will just want, I just want to denote it by absolute value of K, if that's okay. So this is, I will use interchangeably both notations, if that's okay with you guys. So in other words, another formulations of another way to write Brun-Minkowski inequality, maybe a little bit shorter, is just like this. Are there any questions about the Brun-Minkowski inequality so far? So in other words, if we go back to our, for example, triangles, if this is my K and this is my L, we agreed that we get a hexagon as their sum, and the volume of this hexagon raised to the power 1/2, because I'm drawn here on the plane, is bigger than the volume of K to the power 1/2 plus the volume of L to the power 1/2. Actually, the volume is the same. Right? So in a way, the volume of this hexagon to the power 1/2 is bigger than the volume of the triangle to the power 1/2 times 2. Or in other words, the volume of this hexagon is bigger than 4 times the volume of the triangle. Which you can also verify in some toy way, if you like. I'm just explaining it as an example. So this is a Brun-Minkowski inequality. Are there any questions about the Brun-Minkowski inequality?
No, I have one.
Yes.
Is it also the balls that saturate this inequality?
Yeah, so this is a very good question. When is the equality cases? So this is excellent question. Thank you so much. So here is the comment indeed that equality in the Brun-Minkowski inequality happens if and only if K and L are dilates. If K is a dilate of L for some number A. So if K and L are, let's say, the same, but dilates, that is when you get equality. And that's if and only if. Thank you so much for your question. You can verify that dilates do have equality here because if K is AL, you see then you get A plus 1 time. So let me not right here, sorry. So note that if K equals to AL, then K plus AL will be actually just A plus 1 times K, let's say. And we have the volume of A plus 1 times K to the power 1 over N. It's A plus 1 to the power N times the volume of K. All of this to the power 1 over N. So actually it's just A plus 1 times the volume of K to the power 1 over N. On the other hand, on the left, so this is my K plus AL to the power 1 over N, right? Now, this is the left-hand side, right? Now, on the right-hand side, you have volume of K to the power 1 over N plus the volume of L to the power 1 over N is the same thing once again. So in other words, this 1 over N power makes a lot of sense in view of the homogeneity of the back measure. I wanted to write out this to once again emphasize this. Any questions about this? So this is, maybe let's leave it as a little homework that actually it's if and only if. It's a difficult homework. That there is no other equality cases, but there isn't. Okay, so let's move on a little bit. This is a Brun-Minkowski inequality. Let's state two reformulations of this inequality. So reformulation number one, that outlines Brun-Minkowski as an important concavity principle, and this is the central theme of our course here, reformulation of the Brun-Minkowski inequality. Is the following. Suppose lambda is a parameter between 0 and 1, and K and L are sets in Rn. If I take lambda K plus 1 minus lambda L to the power 1 over N is bigger than, I'm going to get on the right-hand side because lambda will come out in power 1 due to homogeneity. Lambda K to the power 1 over N plus 1 minus lambda L to the power 1 over N. So in other words, you can say that volume to the power 1 over N is concave in Minkowski addition. So you can say that the back measure is 1 over N concave, or the back measure raised to the power 1 over N is a concave functional on the collection of sets. Because of this, Brun-Minkowski inequality, from my perspective, is sort of the cornerstone of convexity. When people talk about convexity, for me, it's always about convexity properties of measures. And Brun-Minkowski inequality, it asserts a very fundamental property of the back measure, that the back measure is a concave functional. So this is something actually very deep. So this is the first reformulation. Let me now make another reformulation. So another reformulation will say that, again, lambda is between 0 and 1. Lambda k plus 1 minus lambda L is bigger than the volume of k to the power lambda times the volume of L to the power 1 minus lambda. So this is one more reformulation of Minkowski inequality. Let's call this star and this double star. Let me recall silly old inequality about numbers, that if you have a and b positive numbers, p a number bigger than 0, then also lambda between 0 and 1, then lambda a to the power p plus 1 minus lambda b to the power p to the power 1 over p decreases in p. So in other words, if p is bigger than q, bigger than 0, then lambda a plus 1 minus lambda b to the power p to the power 1 over p is going to be bigger than or equal to the same average, but with q. And when p and q go to 0, this quantity actually becomes a to the power lambda b to the power 1 minus lambda. So this corresponds to taking lambda a to the power 0, 1 minus lambda b to the power 0 to the power 1 over 0, informally. And this quantity is the smallest of this family. So in view of this, because of this, okay, let me, therefore, k lambda k plus 1 minus lambda L volume, it's bigger than or equal to lambda volume to the power k to the power 1 over n plus 1 minus lambda volume of L to the power 1 over n to the power n. And this is going to be bigger than volume of k to the power lambda times volume of L to the power 1 minus lambda, just by applying this inequality to a equal to the volume of k and b equal to the volume of L, right? So in other words, inequality star implies inequality double star. So you see in this multiplicative formulations that I wrote here, multiplicative formulation follows from this additive formulation that I wrote above. However, I'm claiming that actually the two formulations are equivalent, and in fact, double star also implies one star in view of homogeneity, in view of the homogeneity of the volume. I will leave it as a homework, and I'm sure that you will discuss it with Stephanie. Cool. So are there any questions about Minkowski inequality so far? This is more or less all I wanted to say before we move on to actually proving the isoperimetric inequality at long last. Questions, comments? I'd really like to hear from you guys. Once again, I remind you that you can open this board in the browser and you can scroll up and down in the browser and see everything that was written, so that you don't have to just rely on looking at the screen of the Zoom, of course, where not everything appears. So here's part 3 about verifying the isoperimetric inequality from Brun-Minkowski. Of course, we haven't brought Brun-Minkowski inequality, but we will soon. So Brun-Minkowski implies the isoperimetric inequality. Does anyone have any questions? No? If not, we will proceed. So proof. I can remind you, the isoperimetric inequality claim is that the perimeter of K divided by the volume of K to the power n minus n over n is bigger than the perimeter of the ball divided by the volume of the ball to the power n minus 1 over n. This is our isoperimetric inequality, and you remember that it's equivalent to saying that if we prescribe the volume of K, the perimeter is minimized when it's a ball. So proof. Let's recall that the perimeter of K is defined by definition as limit when epsilon goes to 0 of the volume of K plus epsilon ball minus K divided by epsilon. So in other words, it's limit of the volume of K plus epsilon ball minus the volume of K divided by epsilon. Do you agree? So we want to estimate this creature from below. What shall we use? Any suggestions? Anyone?
We use the Brun-Minkowski for the
Exactly. Yeah.
oh no, for the volume of K plus epsilon times ball.
Exactly. So Brun-Minkowski inequality tells us that the volume of K plus epsilon ball is bigger than volume of K to the power 1 over n plus the volume of epsilon ball to the power 1 over n altogether raised to the power n, right? Which is the same as this quantity. If I pull epsilon out, again by homogeneity, this follows, right? So I can continue writing here, bigger than or equal to, lim inf when epsilon goes to 0, here volume of K Yes, do you agree? Now let's recall very briefly something that's called Newton's binomial. Right, Newton's binomial. Newton's binomial tells us that if I have a plus b to the power n, let's say, is a to the power n plus n a to the power n minus 1 b plus and choose 2 a to the power n minus 2 b squared plus so on. It ends at b to the power n. You guys remember vaguely Newton's binomial, right? So in particular, this means that if I take volume of k to the power 1 over n plus epsilon times the volume of the ball to the power 1 over n to the power n. It's volume of k plus n times the volume of k to the power n minus 1 over n times the volume of the ball times epsilon plus n choose 2, this guy to the power n minus 2 over n, volume of the ball squared epsilon squared plus so on. Right, that's what we get. So in summary, I get here actually the volume of k plus n times the volume of k to the power n minus 1 over n times the volume of the ball times epsilon plus something that's O small of epsilon. You remember that we have epsilon going to 0, so everything that's epsilon squared, epsilon cube, and so on actually equals to O small of epsilon. And with that in mind, I can continue writing here equal inf when epsilon goes to 0 of volume of k plus n minus the volume of k over epsilon, right? I'm just repeating this line. Does this make sense?
Yes.
Cool. So from here on, of course, now we can cancel out volume of k, divide by epsilon, take the lim inf, and say that this equals to n volume of k b to n. Right, and this was, where did we start? Let's see, we started with perimeter of k. There you go. So perimeter of k is bigger than or equal to this guy. So we conclude that the perimeter of k divided by the volume of k to the power n minus 1 over n is bigger than or equal to n times, wait, I forgot, I apologize. Here, of course, wow, I'm sorry, I made an error multiple times and nobody corrected me, which is not good. You guys should correct me. Of course, of course, of course. We have to have 1 over n. It was just an arithmetic error that I now corrected. So all that remains to see, it remains to note that n b to n to the power 1 over n is actually equal to the perimeter of the ball divided by the volume of the ball to the power n minus 1 n over n. So one way to see it quickly without studying volumes of balls is actually look through this chain of inequality, asserts that equality occurs in the Minkowski inequality here that we used when k is a ball, because remember that and thanks to somebody's question, we discussed it, right? In Minkowski inequality, we have equality if the sets are dilates. So if k itself is a ball, we have equality, and we have equalities everywhere, everywhere, everywhere. So if k is actually a ball, then what we have here is equality, right? So here, indeed, if k equals to the ball, we have equality in the chain above. And this proves that for the ball, that's exactly what perimeter of B2n over B2n to the power minus 1 over n is. But also you can, alternatively, you can verify this fact separately. So this can be shown this, I will leave as a homework that you can also discuss with Stephanie. And this finishes the proof of the Minkowski inequality. That's the perimeter of K, scaled appropriately by the volume is minimized when K is the ball. Are there any questions about this?
So I was under the impression that since the equality case for Minkowski holds for any set, so you take K, L is a rescaling of any set.
Correct.
You could, I don't know, maybe I'm saying something very imprecise, but maybe you could define a perimeter with respect to any general perturbation instead of perturbing with a ball.
Ah, amazing question. Yeah.
And then
yes.
this would hold, or am I?
Yes, you're up. Well, so it depends on. So you're saying that you can do the same exact argument and obtain an inequality where you replace K, where you replace the ball, sorry, with some other set.
Yeah. And then it would be the perimeter with respect to this set.
Exactly. Okay. Very, very good question. So remark. Let's make a remark. Sorry. What is your name? So answering.
Yeah.
Yeah.
It's João.
Say it again. Sorry.
João.
Yeah. Okay. I'm sorry. I'm not able to. Okay. Let me look on Zoom because I'm not able to write this from hearing. Let me look. Disciplines. Joe Miguel Machado, נכון? Yes? Okay, good. So, okay. Right? There is no one else. Okay. So answering to you, indeed, one can also define an so-called anisotropic perimeter. Not with respect to a ball, but with respect to any set. Right, so this will be like perimeter with index L of K, which is lim-hinf when epsilon goes to 0 of the volume of K plus epsilon L minus K over epsilon, right? And also get an inequality. So yes, this is indeed absolutely correct. This inequality is called Minkowski's first inequality, or isoperimetric inequality for anisotropic perimeter. And this is something that you will discuss with Stephanie. So yeah, so this is something that you will discuss with Stephanie, and you should ask her any questions about this. Perfect. This is very, very good question. Moreover, not only is there this Minkowski first inequality that corresponds to what you said, there's actually a whole family of inequalities. There is a lot there. My general goal is to move into direction of inequalities with functions, but there is a lot to discuss about Minkowski inequality isoperimetry itself, of course, as well. Thanks for your question. Are there any other questions? So how much time do I have, by the way? I hope I have more time, right? I have another 7 minutes or no? Somebody please clarify to me. I was told that it's 1 hour, right? But maybe it's 50 minutes. I don't know. Should I stop now? Who is the boss here? There needs to be somebody who is watching for time. So because I want to know whether or not I want to discuss another little thing, but I could also just discuss it next time. I don't know what's optimal. Are you guys tired? What's can somebody tell me? Sasha, Victoria, anyone?
Галіна, а я можу продовжити, скільки потрібно?
Скільки в мене є часу?
Ну, у вас є час, всі люди на зв'язку, і я можу продовжити навіть годину. Скільки вам потрібно?
Годину. Ну добре, тоді ще десь 5-10 хвилин.
Ми і стартували пізніше, то я думаю,
пізніше, тому можна. Ну добре, чудово. Тоді ще 5-10 хвилин, окей?
Sorry, may I ask a question?
Yes, absolutely.
So in the Brand-Minkowski inequality, the sets are like arbitrary or like Borel or Lebesgue. So what are the class of sets?
Very good question. So Brand-Minkowski inequality, the sets have to be Borel measurable. I didn't dwell on it, but I mean, you can also assume that they're Lebesgue measurable so that their sum is also Lebesgue measurable. The thing is that in principle, if you have Lebesgue measurable sets, it's not guaranteed that their Minkowski sum is Lebesgue measurable. But if they're Borel measurable, it is guaranteed. And that's why it's just easier to assume that they're Borel measurable. But again, this is a collection of questions that I don't want to like ultra focus on. So yeah, let's say Borel measurable. Any other questions? Cool. So let's move on to little tiny bits that I want to discuss in order to set ourselves up for the next lecture. So part 4, log-concave functions and measures. So in order to prove Minkowski inequality, we will not prove Minkowski inequality, we'll actually prove something more general. So we will prove Minkowski inequality by proving a more general, amazing, useful inequality. Let me recall the following definition of a log-concave function. So a function f is called log-concave. F f is a function from Rn into R. If its logarithm is concave, if log f is a concave function, in other words, for any x and y in Rn and for any lambda between 0 and 1, log f of lambda x plus 1 minus lambda y is bigger than or equal to lambda log f. This is definition of concave function, I'm reminding you. Or in other words, if you take the logs out, f of lambda x plus 1 minus lambda y is bigger than or equal to f of x to the power lambda, f of y to the power 1 minus lambda. Let's restrict ourselves to non-negative functions here, by the way. So this is the definition of log-concave function. Let's consider some examples. So if K is a convex set, meaning that for any pair of points x and y in K, and for any lambda between 0 and 1, lambda x plus 1 minus lambda y, point on the interval between x and y, is also in K. So if I have a set K, such that whenever I take a pair of points in it, the whole interval is still in the set. That's when we say that the set is convex. All right, so for instance, a set like this, where I would have a pair of points x and y such that not the whole interval is in K, would be not convex. But the set which I drew above is convex. So suppose we have a convex set, then f of x, which is a characteristic function of K, is log-concave. So if I have, let me remind you again what's a characteristic function just in case. Something weird is going on with the pencil. Function that takes value 1 if x is in K, and 0 if x is not in K. characteristic function of K, is log-concave. Another classical example that we love a lot is the Gaussian measure. Density e to the power minus x squared over 2, like this. This is a classical example of a log-concave function. And more generally, if I take any convex function v, so a convex function is something that looks like this. V of lambda x plus 1 minus lambda y is bigger than or equal to lambda v of x plus 1 minus lambda v of y. So in other words, if I have a pair of points x and y, I take some point in the middle, the value of the function, sorry, the function, sorry, this is concave, so I want to say like this. The value of the function at the midpoint is smaller than the midpoint of the values. That's what a convex function is. And e to the power minus v, e to the power minus convex function is what's called a is a log-concave function. So that's the concept of log-concave function. Any questions about this? Let me now formulate the definition of a log-concave measure. So mu on a random measure is called log-concave It's called log-concave if for any pair of Borel measurable sets K and L, and for any lambda between 0 and 1, mu of lambda k plus 1 minus lambda L is bigger than or equal to mu of k to the power lambda, mu of L to the power 1 minus lambda. So the measure is called log-concave if it is log-concave with respect to Minkowski addition. So let me finish today's lecture with the following theorem, which is called Borel's theorem. Theorem of crystal Borel that says that a measure mu on Rn with density, no, not like this, a measure mu on Rn is log-concave if and only if it it has a density either on Rn or in an affine subspace. F, and F is a log-concave function. So to put it simply, log-concave measures are measures whose densities are log-concave functions. It's not at all obvious, and clearly the theorem actually implies Minkowski inequality. So note maybe I need to switch the pencil. While I'm dealing with the pencil, we're almost done with the lecture. Let me just Anyway, let me just finish here, and we will start lecture 2 tomorrow here. But note that Borel's theorem implies the Brun-Minkowski inequality. That's it for today. Now, please ask me your questions. I would really appreciate if you guys had questions, and I'll be very happy to answer. Any more questions? Let me share again this screen. So as I said, you can scroll up and down on this link.
I have a question about this anisotropic perimeter you mentioned. Like,
yeah.
Is there any natural reason why, like, our natural notion of perimeter is captured precisely by the perimeter defined with balls and not with other some other set, for example, like a cube or something else?
Well, so the thing is that there is many ways to define distance, right? And define norm, define distance in space. So, however, there is one distance that is what we intuitively think of as distance, and that's the Euclidean length, right? Of all the ways there is, for example, many of you are probably familiar with Manhattan metric, which is a way to define distance on roads of cities such as New York, where distance is the number of blocks you need to travel to get from point A to point B. You can say that it's a natural distance if you're traveling in New York, but in principle, intuitive distance for all of us is always a Euclidean distance. And the unit ball of that distance is the ball here. So the ball is what corresponds to Euclidean distance. And so because of that, the most natural intuitive notion of perimeter to all of us is exactly like this. It's a measure of points, which are distance epsilon to our set, divided by the width of the strip, divided by epsilon. And the distance here is the most natural thing. Oh, one should also mention that, of course, this classical perimeter, it has many nice properties that an isotropic perimeter might not have. There are contexts where you can study both, and there are contexts where only the classical perimeter is sort of the nice guy for us. But yeah, the short answer is that the way we think of distance, the most natural way to think of distance is Euclidean length. Let me finally write that remarks that Borel's theorem implies Minkowski. Did I answer your question?
Yes, thank you.
Thanks for your question. Are there any other questions? I'd be very happy to, obviously, to answer. I'd be very delighted. So if there is no questions, I'll email the homework, and I guess you should post the homework on the website. It will include everything that I wrote here. It's already, I think, in the homeworks on the notes. And there'll be some additional homeworks, and yeah, maybe with Sasha we can talk a bit, and he could clarify to me a bit more questions about how I should assign the homework. The notes that we have used right now will also be posted, hopefully, on the website, as well as the LaTeX notes. So yeah, I guess we can stop the recording here, and maybe if somebody is afraid, they can ask questions after that.